Steinhauer here. Welcome back. Talking about dark matter, we've decided that it's a real thing in all likelihood. So now let's think about what it could be. What is it that is 85% of the matter of the universe that we have not yet been able to detect and isn't emitting any visible light? And we can only see that it's there by the gravity that it's exhibiting on its surroundings. So there's two basic options of what that dark matter could be. It could be ordinary stuff. It could be what we call baryonic, made of protons and neutrons and ordinary matter things. What could be made of those things and have a lot of mass and not be emitting very much light? Well, things like black holes, very massive objects that are not emitting any light. Things like neutron stars, very massive objects that are very small and therefore not emitting very much light. Things like brown dwarfs, not very massive and on stellar scales, but not emitting much light, and there could be a lot of them out there. Collectively, we call these things massive compact halo objects, or for short, MaCHOs. Because these are compact halo objects, black holes, neutron stars, brown dwarfs, that are in the halo of the galaxy. And so the other option is that this is not baryonic matter, that this is some other kind of thing, perhaps some neutrino-like particle that doesn't interact with, that has no charge and therefore interacts not at all with photons or light. And if it's not neutrinos, we know we've measured the number of neutrinos out there and there aren't nearly enough of them to be able to explain the dark matter. But what if there were another kind of particle that we haven't yet discovered that is massive, and there are a lot of them out there, that could potentially explain this phenomenon? And of course, these are known as weakly interacting massive particles, or WIMPs. So this is a contest between the MaCHOs and the WIMPs. So let's take a look at both of these in turn and see if we can make some observations that will tell us which direction to go in. First of all, let's think about the MaCHOs. There are ways to tell if MaCHOs are out there, even if we can't see them directly. And one of the ways to do that is by looking at the gravitational lensing. So we know we live in a galaxy. We know that there are billions of stars in that galaxy. If 90% of the mass of the galaxy is made up of these MaCHOs, there should be lots of them out there. They should be everywhere. And it should happen that periodically, one of them will pass right between us and a more distant star. And if that happens, an interesting thing happens. You might think that this star might seem a little bit fainter while that MaCHO was passing by and potentially blocking it. But what actually happens is there's actually more light reaching us from that object, because some of the light that would have missed us, like for instance this, now is bent around that black hole or whatever it is, that compact object, and now does reach the Earth. So it turns out that if you've got a star and a black hole, let's say, passes between us, that star will appear brighter as that object is moving by, because more of the light will be directed towards us. This is a gravitational lensing effect. So we can look for this. All we have to do is stare at a bunch of stars and look for them to get brighter. And sure enough, we see it happen. Here's an example of one of them from 2006, where you see the light curve at the top here. Let's take a look at what we're looking at. This inset here is the light curve. It means how bright the thing is as a function of time over several years. And you can see this star isn't changing in brightness at all. It's perfectly constant. This is just a unit of magnification, meaning how much brighter it looks than normal. And you can see that that's 1. That's no brighter than normal. Until this very interesting event here in 2005 or so, where this thing gets a lot brighter all of a sudden. And this in the bottom is a zoom in on how that brightening actually happened. And this is exactly what we predict will happen. And the shape of this thing will be if you've got some compact object moving in front of it. This is a particularly interesting object because we were not only able to detect the presence of this star and the object that went by it, but we were able to detect the existence of a planet, I believe orbiting this star, but it could be orbiting the compact object. I'm actually not sure how that works now. Anyway, this is an exciting discovery, right? We've discovered not only a compact object that's passing in front of the star, but also some planet that's associated with one of the two systems in this object. But this doesn't happen very often. This is a pretty rare event. And it would need to happen really regularly in order for the entire mass of the galaxy, or 90% of it, to be explained by these massive compact halo objects. So we're many, many orders of magnitude below the limit that the level that we would need to see to explain dark matter. So it doesn't seem to be the MaCHOs. The MaCHOs make a lot of noise, but there aren't enough of them out there to be able to explain the dark matter that we see in the galaxy. So we're left with, it's probably WIMPs. It's probably some axion-like, neutrino-like particle that we haven't discovered yet that is the primary component of mass in the universe. And this is, they're probably running around, they're probably, confined to the galaxy in some level, but spread fairly evenly throughout the galaxy and moving through us as we speak, but just not interacting at all with the planet or the sun or us at all. We can only detect them by the gravity that they emit. Okay. Next question we want to ask is, what is the distribution of galaxies in space? Are they randomly and fairly evenly distributed? Did they come in clumps? Let's ask and answer that question. So let's talk about the local region of the universe first. The Milky Way is a member of a group of galaxies called the local group. There are three primary members of this galaxy group. The Milky Way and the Andromeda galaxy are the two biggest members of the local group. But the Triangulum galaxy is a third spiral galaxy. There are three spiral galaxies in the local group. The Andromeda galaxy is actually the biggest, followed by the Milky Way, and then by Triangulum galaxies in the local group. But there are dozens of other smaller galaxies, some of them satellite galaxies to the bigger galaxies, but some of them just sort of out there on their own. The Aquarius dwarf and NGC 185 that are just part of this sort of loose association of galaxies known as the local group. And these are elliptical galaxies, dwarf elliptical galaxies, and there are regular galaxies and things like that. So 54 known members of the local group now, but this is our little region of the universe. When we go out further, we zoom back, we extend our cosmic zoom lens further out, we see larger clusters of galaxies. And now we're talking about hundreds to thousands of galaxies. The biggest large cluster, galaxy cluster to the Milky Way is the Virgo cluster, so-called because it's in the constellation Virgo. And you can see it here. There are a bunch of very large elliptical galaxies, some spiral galaxies. These holes are just regions where we have blocked out local stars that are in the foreground so that you can see only the galaxies in the Virgo cluster itself. And you can see way more dense than the local group of galaxies. There are thousands, hundreds and thousands of galaxies in this particular group, this particular cluster. Here's another cluster, a nearby cluster, the Coma cluster. Again, you got these very bright, large elliptical galaxies. This is a foreground star, but most of the rest of the things in this image are galaxies in the Coma cluster. Thousands of galaxies in all, located in one kind of region of space. When we zoom out even further, so we know the galaxies come in small groups and larger clusters. When we zoom out even more, we see more of the actual distribution of galaxies in the universe. And this is a wedge diagram. We are down here at the apex of the wedge, and this is the radial distance away is distance from the Earth, or redshift, right? It's how fast those galaxies are moving away from us, and therefore also how far away they are. And this is a fairly nearby slice. It's only going out to a redshift of about 0.2, That's the Z parameter that we were talking about earlier. And this axis is angular position on the sky. So this is a wedge slice of the universe looking out in a particular direction. And we can see what the distribution of galaxies is. And even, so you can see some things that look like very large clusters of galaxies here. But the distribution on a whole is made up of this interesting voids and filament structure. So you've got vast regions of space where there are huge numbers of galaxies that seem to lie along these filaments where there's large matter density. And then there seems to be huge regions where there just aren't many galaxies at all. It's sort of like a sponge in that you've got these big holes and the galaxies seem to be dispersed in filaments, and the galaxy clusters and the superclusters tend to be arranged in the filaments that surround these big voids of emptiness in interstellar space. So on the biggest scales, that's what you get. This is much easier to see on an animation. I've got a nice video posted in the supplemental materials below where you can see both how the matter is distributed in a three-dimensional sense, because it will zoom around, and also how that distribution has changed over the course of the age of the universe. So take a look at that. Okay, we'll come back in the next video and start chapter 29, the Big Bang. Where are we in terms of understanding the beginning of the universe and the conditions that were like that? See you then.